In this video, we're going to combine some of the techniques of probability along with some of the more advanced counting principles. I've got a couple of examples to illustrate this. A password of length 8 we're going to create from the letters A through Z. We're going to assume that we're just dealing with lowercase, or all uppercase, it doesn't matter which. We want to know what the probability is that, first of all, no letter is repeated. Second of all, that we want the probability that the word chair appears. And we also want to worry about what the probability is that the letter P appears exactly 2 times. Let's look at the first example. Before we do that, though, we need something very important. We need to know how many passwords are possible overall. Because what we'll do, if you remember, when we do this, we want to find the probability of our event, or the probability of our event E, is the number of elements in our event E divided by the number of elements in the event S, or in the sample space. You may have also, instead of seeing this notation, you may also see something that looks like this. N of E, the number of elements in E, divided by the number of elements in S. Well, how many passwords are possible? There are 26 to the 8th passwords. Why? Because what I do is I imagine these 8 slots. 1, 2, 3, 4, 5, 6, 7, 8. And then I have free choice of any letter in A through Z. So I might choose first to be a P, and then maybe an R for the second letter, and an O for the third, and so on. That's just one of the possible 26 to the 8th outcomes. Now, I didn't compute this number because it's very, very large. Now let's focus on getting no letter repeated. Well, if no letter is repeated, what we want to do is, again, we want to imagine those spots. There's 4, 5, 6, 7, 8 spots. We can pick any of the 26 letters we want for the first spot. So as a sample, let's suppose we pick J as our first letter. Okay. For the second letter, we can pick any that we want. Maybe we'll pick an O. We can't pick a J again, so because there were 26 choices for the J, there are actually only going to be 25 choices for the O. Well, now I've chosen the J and the O. Let's choose a B. There are 24 choices for what letter comes third. And then there would be 23 and 24, or 22, and so on. And one way we can denote that, you may not be familiar with this notation, is it's 26 permute 8. That's one way to look at it. One way to denote this is 26 factorial divided by 18 factorial. What do we mean by factorial again? Remember, that's the product of all integers from 1 up to that number. So we go from 1 to 26. We multiply all those numbers. Now, why does this work out to be the number we're looking for? Well, we would first take, we'll look up here at the top, 26. We would multiply that by 25, by 24, by 23. I need to do this until I get 8 factors. I'm only at 4 now. 22, 21, 20. I think I'm up to, I'm at 7, and now I'm at 8 numbers. That product turns out to be the same as 26 factorial over 18 factorial, because what we do is this is like the beginning of 26 factorial. When we divide by 18 factorial, it wipes out all those extra factors. So the probability that we don't repeat is the number of permutations of 26 things taken 8 at a time. That's the way we read that, which is this number, divided by the total number in the sample space, which is 26 to the 8th, which I used a calculator and got it's about 0.3016, about a 30.16% chance. So the second question was, what's the probability that the word chair is in our password? Okay, now chair is a 5-letter word, and so there are only 4 ways that chair could appear. We could have chair followed by 3 letters, or 1 letter preceding chair followed by 2 letters, or 2 letters chair and a letter, or 3 letters and then chair. So there are 4 possibilities for this guy. Okay, and then we need to figure out how many ways I can select those letters that are remaining. Well, notice in each case there are 3 letters to be chosen, right? So the passwords containing chair, there are 4 because we want to choose one of these 4 different arrangements. And then I have 26 letters for the 3 question marks that I have here. So that'd be 4 times 26 times 26 times 26, or 4 times 26 cubed. Now, you might say, well, how come I can repeat the letters? Now, we've moved on to a separate problem, so because it doesn't say that letters can't be repeated, I use 26 to the third. And so the probability that chair appears, that's just the way I'm going to write this, is the number in our event, 4 times 26 cubed, divided by 26 to the 8th, which is a really, really extraordinarily tiny number, 3.37 times 10 to the negative 7th, which, if you really want to write it, is 0.00000, oh my goodness, one more 0, 337. Okay, as a percentage, that's 0.0000337% chance. Not very likely at all. Our final example was when we have exactly 2 P's in our password. Well, there's 5, 6, 7, 8. Often in these problems, the best thing to do is attack the most specific piece of information first. And we want to make sure that we have 2 P's. Well, the 2 P's can go in any of these 8 slots that we have here. Let's just suppose that I choose this guy to be a P and this guy back here to be a P. In how many ways can I do that? Well, we have the answer written here. It's 8 choose 2. Why is it 8 choose 2? When I use the choose function, I really want to think that order does not matter. Well, it seems like order matters because I've got a P in the 3rd spot and the 7th spot, but that's not the order we're talking about. The order we're talking about is the order in which I selected the 3rd and the 7th spot. I want to, out of these 8 spots, pick 2 of them. I could have chosen the 3rd and then 7th, or I could have chosen the 7th and the 3rd. Neither order really matters. That's where order is irrelevant. Now, for the remaining letters, I can choose any letter I want except P. So maybe this could be a B, and then a Y, and then an O, and then a R and an O, and a D, and a T out here. For each of these spaces that didn't have a P in them, there were 25 choices, so that's 25 to the 6th. So we're going to take our event calculation, the 8 choose 2 times 25 to the 6th, and divide it by 26 to the 8th. And we end up with about a 0.0327% chance. I'm sorry, a 0.0327 probability, which is a 3.27% chance. Okay. Well, let's look at another example. We have a committee of 7, and we want to create this from a group that contains 12 women and 10 men. Have various things we want to know. What's the probability that exactly 5 women are on the committee, or at least 2 women are on the committee? Well, first of all, we need to know how many committees are possible. Well, the committees don't, in general, have any specific restrictions as to how many men and women can be on it. There are a total of 22 women and men. We want to pick 7 of them. Does the order matter in which I select the men and the women? It does not. It doesn't matter because if I say I'm going to select Bob and Sally and Hank and so on, it would be the same as if I said I'm going to select Hank and Bob and Sally and the rest of the people that I didn't mention before. Okay, so the order in which I select these 7 people from the 22 doesn't matter, and so again, combinations are, and we're not allowed to repeat. I can't have Hank 5 times, and so we're going to have 22 people. We want to choose 7. This is the calculation for the binomial coefficient, the choose function. And we end up with 170,544 different committees that are possible. So now we want to go back. What if we want exactly 5 women, and what if we want at least 2 women? Well, if we want exactly 5 women, I know that then I'll have to have 2 men because we have 7 people on the committee. We're going to select 5 women. There were 12 women total. We choose 5 of them. We have 10 men total. We're going to choose 2 of them. And we find that there are 35,640 different committees with 5 women and 2 men. So our probability that we have exactly 5 women is this number, the number of elements in the event, divided by the number of elements in the sample space, which is about 0.20898, a 20.898% chance that we have exactly 5 women on the committee. For the second one, we want, what's the probability that we have at least 2 women? There are a couple of ways we could do this. One, in order to have at least 2 women, we could say, oh, well, we have 2 women, or we could have 3 women, or we could have 4 women, or this is going to take a long time. And so instead, I look at, well, what happens if I don't have 2 women on the committee? Well, then I have either 1 woman or no women whatsoever. And so what we'll do is we'll take all of the different committees that are possible and take away the number that have no women or 1 woman. Well, the total, remember, was 170,544. To have no women, that means all 7 of the people on the committee are men. There are 10 men. We want to choose 7. That's the case when we have no women. When we have exactly 1 woman, out of the 12 women, we want to choose 1 of them, and then the remaining 6 people need to be chosen from the 10 men. Okay, which is 167,904. So the probability is going to be 167,904 divided by 170,000, blah, 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 which is about a 98.45% chance. Which makes sense because there are a couple women more than there are men. Now, a common mistake in this particular example, part B here, is to say, oh, let's do this. Let's just go ahead and then pick 2 women and then fill in the rest. Right? So if I pick 2 women and then just say, okay, everybody else, let's get in this group. I've got 5 more people to choose. Let's just go ahead and choose those. The reason this doesn't work is because when you pick 2 women, you make them special in some way by choosing them first. Okay? And here's an example of why this might not work. Let's suppose when I pick the 2 women, I pick Molly and Nicole. And then when I fill the rest of the committee, I have, let's say we have a total of 5 more people to pick. Let's suppose I had 4 men. And then the last person I pick happens to be Ophelia. If I were to look at another possibility, I could get this same committee by doing the same selection process, and that would overcount the total number of committees that have at least 2 women. How could this happen? Well, this could happen if I say, oh, well, let's pick 2 women. Maybe I pick Molly and Ophelia, then I pick the exact same 4 men and Nicole with that group of 5 people. So your group of 5 people may be comprised of different folks, but this person and one of the original 2 women that we chose might be the same one.